me. Okay, I give you this busy sheet, guys. You should have it right in front of you. When it comes to the power system in any building, the power system in any building starts with a transformer. The transformer is the start point for any power system. There are two types of power system, Adam, that you're going to have. You guys have, that's the first sheet. Power system that's higher than 600 volt, and power system that less than 600 volt. So what I did, I have 5 systems here. I know it's a busy sheet. System 1, System 2, System 3, System 4, System 5. These are the typical system that we use in the US when we deliver system to buildings. So the first system, guys, it's a 7200. Can you guys see that? 7200, 28120, the first one. This is single phase, typically used in residential and light commercial, and we typically use it up to 800 amp. That's the first system. So if you have a commercial building, light commercial building, or residential building, most likely you're going to have a system that's coming out of a transformer single phase, primary 7200, secondary 28120, right in here, 28120. I'm sorry, 24120. And it's single phase, and it's going to be feeding residential and light commercial up to close to up to 800 amps. Sometimes they go higher than that. So that's system 1. System 2, we have a 240, 120 center tap delta. What they give you on the primary side, they give you 13,800 volt. Can you see that? On the secondary side, they give you 240, 120 center tap delta, they call it. And I know you guys have got it. The one who came from electrical, you guys did calculation on this. It's a 3-phase. So what we do, we use commercial plus light industrial. We use it, guys. If you have a load up to 10% single phase and the 90% 3-phase, this is typically what we use this system for. 10% single phase, and the rest is 3-phase. You can use it very high, up to 1600 amps, and these are all suggestions for the system they use. This is a delta center tap. Can you see how they center tap it right in here? Delta center tap. Okay, the second system that we use, so that's my system. The second 3 system that we use, guys, in the US, these are the most common system in a commercial industrial building. System number 1 is they give you 13,800 volt on the primary. On the secondary side, they give you a 28120. That's the system that we're using. It's a 3-phase system. Typically, if the building is typical, a commercial building, square foot of 15,000 or less, we recommend this system, like the building that we have, guys, and it's used for residential risers, commercial, light industrial, up to 4,000 amp. The reason why I'm saying you this, guys, you're designers, not just drafters, so you're going to be in a meeting one day when you become a project manager, and they will be asking you to decide what type of voltage system do we need for this building. So these will be, they will get you kind of a rough ideas. What are the type of the system that we use? So square foot, 15,000 or less, residential, light risers, downtown Minneapolis, all these risers that you do, commercial plus light industrial up to 4,000 amp. Then we move into system number 4, guys. System number 4 is 13,000 volt, 13,800 volt on the primary. On the secondary, we have 48277, 3-phase. This is heavy commercial and industrial. If your building is more than a 15,000 square foot, can you just see that? That would be a good recommendation. And the last system, I haven't seen a lot of it here. The last system, we have a 13,800 volt on the primary. On the secondary, 600/347 volt. It's a 3-phase, very large industrial plant. They use system like this, not commonly used. So these are the 5 most common power system that you're going to encounter. The 5 most common power system you're going to encounter. One more time. You start with the first one, residential 24120. The second one is 24123 phase, typically commercial industrial with only small amount of load single phase. The most common ones, guys, in the US that we use, the most common ones in industrial commercial are number 3 and number 4. The most common ones are number 3 and number 4. You can see that it's 28120 and 48277. These are the most common ones. Derek, I gave you a copy of that one. You have it in front of you? Okay. So these are the most common ones. So everything I give you here is just ideas. Where do we use this system? Any comments, any questions? All these systems, Derek, my friend, they're called low voltage services, 600 volt or less. You're feeding everything here from a 600 voltage or less. These are the power systems that we use in the US. Comments, questions, typical power systems? Okay, why did I start with this? Because we're going to do some calculation on the most common ones, some calculation related to it. Okay, now remember, this is low voltage. If you go to the next slide, guys, this is a higher voltage. What they do is high voltage. You guys also have a copy of this. I call it high voltage service, more than 600 volt. Where do we use a system like this? I don't know if you worked in at the airport, right, in Minneapolis. They use system like this. So they call it higher than 600 volt. What they do is if you have multiple buildings, if it's a campus and you have multiple buildings, good example, 3M, University of Minnesota, Mayo Clinic, these that have multiple buildings that they own and operate. One service, one owner, multiple buildings. This is typically what they do, guys. What they take is they take a high voltage and they take a feeder from a switchgear and they one feeder per building, and they take all these feeders and they feed their buildings. Typically, so you get your voltage 69,000 volt into a switchgear. From the switchgear, typically delta, you convert it down into 2.4 or 4.16 or 13.2, or the most common one, Adam, the most common one that you're going to be dealing with is something called 13,800 volt. That's the voltage that they use. So they take it and they bring it to a switchgear, guys. Here's my 13.8 coming from the transmission line here. I don't know if you can see it down coming slightly. So I have my transmission line bringing my 115 or 69,000 volt into, so that's my transmission line. You have a transformer here. So you get your transformer, you transform it down. So you have to have some type of a transformer here. Transfer the voltage down into 13.8, 2000 amp, and you take 1, 2, 3, 4, 5 feeders. You take them and you feed 5 big buildings like Mayo Clinic. Any comments, guys? Any questions about power distribution for over 600 volt? We don't deal. You guys are not going to deal with it here with me. But that's a common practice. They can go up to 4,000 amp. They take the 13.8, guys, then they transfer it down into 4,000 amp, 48277. So, for example, the Conduit building that I worked on, they take a 13.8 to the 13th floor, 13,800 volt cable through the building into the 13th floor, because nobody wants to sit on the 13th floor. And they have a big substation there, guys. You take the 13,800 volt, through a fuse disconnect to a transformer, and you drop it down to 480 volt, 277, and they feed all the chillers and air handling units and what's not. And then another substation, 28120, and they feed all the receptacles and their lights, if typically receptacles. So keep an eye on these voltages when you're at Mashad. They're talking about primary feed for the building. They use a primary feed or high voltage feed. They talk about 2400 volt, or they call it 4160 volt, or 13,200 volt, or typically 13.8 is the most common, 13,800 volt. That's a lot of volt. That's a lot of volt. Any comments, guys? Any questions? You wouldn't specify this feeder for a building like Dunwoody. If you have multi-building like Dunwoody here, you'll have a switch gear, medium voltage, and you give it one feeder. You basically act like utilities. Okay, one more time before I go back to the calculation. So here's the power system, secondary, guys, low voltage, the most common, and here's the power system, primary. So what I did, I took the most common system that you're going to use, very similar to the one that you have, and we're going to do some calculation on it, guys. You guys have a copy of this. So what I do, I have question number 1, I call it. I have a primary delta, secondary Y, delta Y transformer, primary delta, secondary Y, and I need to size the following. Number 1, and the transformer is 480 on the primary, 208, 120 on the secondary, and I need to size the primary conductor coming to the transformer, the primary fuses, the secondary conductors, the secondary fuses, as well as the grounding electrode conductor and the main bonding jumper. Any comments, any questions? You guys have it, right? You have that in front of you. Any comments, any questions? What are we trying to achieve? So they will look up to you guys to size the primary and the secondary fuses and cables, as well as the main bonding jumper and the grounding electrode conductor. What is the grounding electrode conductor? The wire that you take from the center of the Y to the ground. That wire here. What's the main bonding jumper? The main bonding jumper is the wire that you tie the neutral to the ground. There will be a ground log and a neutral log, and you tie them together with a wire. They call it main bonding jumper. And we are to size these 6 things. Any comments, any questions, guys, before we go ahead and start? 2 things. Number 1, this is the most common one. That's what we're going over. Number 2, this will be also on your test, guys, next week. So be aware that it's a very similar example. I have 2 examples I'm going to go over. You're going to see it's so easy, very easy, straightforward. So grab your calculator, get yourself handy, and let's go do some sizing. Before I move on, any comments, any questions, what we're trying to achieve? We do have a transformer. On the primary side is 480. On the secondary side is 208, 120. It's a delta Y. We need to size the feeder and the fuse on the primary, the feeder and the fuse on the secondary, the main bonding jumper, and the grounding electrode conductor. Any comments, any questions? Comments, questions? Does it make sense? Yes, no? Okay, the primary feeder. So let's go ahead and guys and size. When you get the primary feeder, you go, so I'm going to use black here. My primary feeder is number 1, is called the primary feeder. The first thing you need to do is you need to find the current on the primary side of this transformer. The current on the primary side of this transformer, you take the 1000 kVA and divide it by 1.73 times the voltage on the primary side is 480. That's how you find when we size conductors and fuses, guys, we size them based on the current, not the voltage for the most part, current. Okay, so that's how you find the full load current of this transformer. And if you guys do your math, you're going to end up with 120 amp for this transformer. Okay. Now, if you go to 21.5, the feeder, dot 2A1, this is an EC code book. If you go to 215.2A1, it will tell you guys if it's continuous load. If it's continuous load, size it by 1.25. We're sizing a feeder. Okay, feeder size. Then it's continuous load 1.25. Multiply this one by 120. It will get you a healthy 150 amp. Take this one, gentlemen and ladies, to 310 table. 310.15 B16 under 75-degree column. And that will give you a healthy 3 conductors, number 1 aught, A, W, G. And what type of insulation? Let's just assume that this conductor, guys, was indoor. And let's assume we're going to be using a THHN. So we have 3 conductors. Why 3 conductors? Delta. Does delta need a neutral? Look at the delta. Is there a neutral on the delta side? No. Delta does not need a neutral. Any comments, guys? Any questions? Does it make sense? You have, what's the 215.2A1? That's an NEC code book. NEC 2011. That's the size of your fuse, your conductors. Let's go size the fuse. Any comments, any questions? Any comments, guys, any questions? To size your fuse, before we size the fuse, guys, everybody's good? I'm going to take you to this table. This table is directly from table 450.3b. If you have never been there, grab your code book and highlight it. You need to know how to use it. This table, guys, if you go there, the most important thing about this table for it's stable for transformers, overcurrent protection for transformers 600 volt and less. So this, you can use this one only if the transformer 600 volt and less. And then, if you look at the primary side, guys, the primary side, they tell you primary only protection, primary and secondary protection. Typically, your default is primary and secondary protection. If your amps are less than 9 amps, that's smaller transformers. Our amp is more, I primary is more than 9 amps. So what's the multiplier? Can you guys see what's the multiplier to size the overcurrent protection device? 250. So my multiplier is 250. Any comments, guys? Any questions? Why am I going to multiply by 250? One more time. This table, you use it to size the overcurrent protection device for transformers. This first row is called primary only protection. That's if you only have circuit breakers on the primary side. We will have primary and secondary. Can you guys see that? Look at this. It's not primary. Here's a circuit breaker on the primary and the secondary. So we're going to go where? Then we are under the second row, which is the default. They're telling you guys for the primary current, you multiply 250. For the secondary current, if you're sizing the secondary, what do you multiply? 125. Can I have thumbs up, Chad? We fully understand how to use this table. Yes? Karen? Good? So on the test, guys, you're expected to go to your code book, highlight that test, and highlight it, and use it. Okay, so that's your 125%. One more time. You're going to see me multiplying by 2.5 here because of 2500. You're going to see me multiplying on the secondary side by 1.25 because of the 125%. And I'm going to be multiplying by 2.5 on the primary because of the 2500. Okay? Here's your primary, here's your secondary current, here's your primary current. Both of them have protection. Can you guys see that? I want to bring to your attention, guys, to note number 1. Note number 1, if you read right here, it says, by the way, if you did not hit a standard fuse, you have 3 options. Either you sit and cry, go to the bar, drink, and get mad, or, these are options, or go or sell an arm and a leg, and they'll custom design any fuse they want for you. How many options do we have now? 2 options, because cry and sit and drink is 1 option, or go down. Cool. So if you end up with 5.5, say you end up with 23.5 fuse, they don't make them, you go to 20. Can I get you guys to look at this? Wherever you see note number 1 in the table, that's where you go down, up. Can you guys see that? You go up wherever you see note number 1. Are there any note number 1 here? No. So can you go up here? No. So on the primary side, we go down. On the secondary side, we go up. One more time. On the primary side, we go down if it's not standard. On the secondary side, we go up. Why do we go up? Because this has note 1. This does not have note 1. It's not 3. It's not related to going up. You use this table, guys, if both the primary and the secondary are less than 600 volt. You use this table if your primary and secondary are less than 600 volt. Before I let go with this table, can you guys give me a thumbs up that we know how to use it? Yes? No? In between? Okay. So current less than 9 amps. There are 2 columns here. Current less than 9 amps for smaller transformer, control type and what's not. Typically, mostly going to be in the column that says current more than 9 amps. Okay. Having said that, so on the primary side, my friends, the multiplier that you're going to be using is we have our So primary overprotection device. My multiplier that I'm going to be using is 2.5 multiplied by 120, and that will give me a healthy 300 amp. And if I have no idea what size is this, you go to 248.6, and if it's not a standard, you have to go down. We just said that, and we have it to hit the jackpot here, and my fuse would be 300 amp. One more time. You multiply your full load current by 2.5. It give you 300 amp. 300 amp is a standard. How do I know? Take it to 240.6, and that will get you a 300 amp as a standard. If it was 305, Derek, what do? You go down to 300. See that little arrow here? That's your indication that going down. Why do you go down? Because, gentlemen, if you go to this is the primary. It doesn't say go up. It doesn't have note number 1 next to it. Okay, any comments, any questions? Any comments, guys, any questions? So we size the primary and the second, the primary fuse and the primary conductor. These 2 things done for you. So we go to the secondary side. Now we are done. All what you have to do now, give this to an electrician with conduits and wire, and go wire. Give me a fuse, set of fuses with a disconnect. Bring your EMP conduit, put these conductors inside it, and off it goes. How many of you guys have the calculator? Calculator handy? So grab your calculator. We'll do the second one in the calculator. Okay, so let's go to the secondary side. The secondary side, my friends, the same thing. You need to take 100 kVA, divide this by 1.73 times 208. Anybody knows why we divided by 208 instead of 480? Because the secondary side is 208. That will give you a healthy 278 amp, 278 amp. 215.2A1 tells you guys if your load was continuous, then multiply that baby by 1.25 times 278. That will get you a healthy 348 amps. 348 amps. And then you're going to take your 348 amps, take it to table 310.15 B16, 75 degree column, always, and that will give you 3 conductors number, if you guess the size, 500 K, C, and M, and let's just say they're T, H, H, N because we're indoor. Here's the size of my phase. Straightforward. Dirk, the only thing we did is just multiply by 1.25 because we're assuming it's continuous load on the secondary side. The second thing I'm going to do is the neutral, guys. I need to size the neutral. I'm going to do it in a different color. My neutral feeder. For a neutral feeder, the way, because you don't have what the neutral load is, it's just a transformer. You have no idea what the neutral load. With me, guys, remember when you calculate the neutral load and you went and you sized it based on that load? Do you have idea what the load is here? I don't have any idea what the load is. So what I typically would do is I take the full load amp, which is where we here, 348. So continuous load. But let's take. So take because we size it, take the 348 amps that you size your phases on, the 348 amps that you size your phases on, the first 200 amp, leave them alone. This is from 220.61B, guys, B2. And anything, so then you take 348 minus 200, cut it by 0.5, 0.7, let's say 0.7, add them up, and you're going to end up with 304 amps, 304 amps. Then take the 304 amps, take it to the same table, table 310.15 B16, and that will get you a healthy conductor. One conductor, number, what size did we come up with? One conductor, 350, 300, yep, always, 350 kcm THHN, 75 degree. Any comments, guys? Any questions? So that's how I size my neutral.
So you did 348 minus 200 times 0.7, right?
Yep. Plus the 200. You have to add the 200 at the end after you did it. Yeah. The first 200, leave them alone. Anything higher than 200, add them up. The last one, guys, that we're going to do is secondary overcurrent protection device. If you guys go to table 450.3b, we were just there, it will tell you that you take 1.25, multiply that baby by the 278 amps. That will get you 348 amps. And then you take the 348 amps, take it to 240.6, like we have done everything else. That will get you 350 amp fuse, and you have to go, no, you don't have to go, but you can go up. So from 348, I don't go down, I go up. Why go up? We're just looking at the table, guys. We said there's not number one that tells you, hey, instead of getting mad, go to the bar, get upset, or custom design yourself a fuse, you can go down. You can go up in this case. This is number 4. Any comments, any questions, guys, about number 4? 2 more things, and when we're done with this example, I have one more example, the same, just kind of to push the idea. Any comments, questions? Okay, so we're going to go, the next one, guys, is called grounding electrode conductor for separately derived system. It's called separately derived system because we have a delta and a Y, and there is no connection. Here's the delta, 3 wires, 4 wires coming out of Y, and there is no connection between them whatsoever. Nothing. They're not connected to each other. Electrically connected. They are coupled together, guys, through electromagnetism. Welcome to the Tesla world, huh? Coupling them together through electromagnetism. That's a separately derived system. So you're supposed to ground and neutral. I will remind you where this one was. If you guys look at this is the wire, comes from the transformer lug all the way down to the ground rod, So that's the wire. That wire, when you size it, very easy. The NEC code book says you're going to size it based on the secondary conductor from 250.66, 350.30A5. All these guys, it will tell you, go ahead and find your 500 kcm. Take this baby to 250.66 and find yourself a number 1 at AWG. This could be THHN or bear. So here's the conductor. Could be a theater chan or bear. Theater chan or bear. Very easy, very simple. We've done it before. You guys have done it with me for the project. By the way, guys, you're going to see 90% of what we do is repetitive. You size the feeders, the fuses, and the main bonding jumper and the grounding interconductor for a building, for a panel, for a transformer, for a motor, for what's not. That's all what we do. Okay, the main bonding jumper, main bonding jumper. There you go. Main bonding jumper. This is the one that takes the neutral and the ground bars and tie them together with a wire. Bond, they call it bonding the neutral. Main bonding jumper. Main bonding jumper is at the service. For the systems, guys, they call it system bonding jumper. They're all the same. One at the service and the other one is a simple drive system. Very identical calculation for them. Okay, gentlemen. So for the main bonding jumper, same calculation here. You take the 500 kcm, take it to table 250.66, and that will get you a healthy one conductor number 1 at AWG. That could be THHN or misspare. I do have a note at the bottom that says if the conductor size is more than 1100 kcm for the main bonding jumper, then you have to multiply by 12.5% of the phase conductors. Write yourself a note. We're going to do it next example. That's only if your conductor, which is the 500 kcm more than 1100 kcm? No. So this note at the bottom does not apply. It applies only if this conductor, and you can see this conductor here, is more than 1100 kcm. Is it? No. So it doesn't apply. All right? That's resizing 6 things for this transformer. If that's not enough for you, we're going to go jump to our next transformer, exactly the same. One more example. Talk about repetitive, huh? One more example. Repeat the same thing. Any comments, guys? Any questions? No comments, no questions. Here's your second example. You guys have it in front of you, right? Everybody had it? Look at this baby. This baby is 4,160 volt on the primary side, the delta. On the secondary side, I have 48277 instead of 28120. The transformer is a 1500 kVA transformer, big boy. And I am to size the same thing. The feeders on the primary and the secondary, the overcome protection device on the primary and the secondary, the main bonding jumper on the secondary, and the grounding electrode conductor on the secondary side. 6 things. Same way. The only thing I want you guys to pay attention to, you see the 4160, since this is a higher than 600 volt, when we size the cables and the fuses, we have to go to a different table. Why? What makes this question different than the one before? Can you guys see the voltage? One voltage is higher than 600 volt. Okay? If you're higher than 600 volt, gentlemen, here's the table. Oops, where's the table that we don't have? Okay, here's the table that we have to go. If you're higher than 600 volt, this is the table that you're supposed to go to. Let me just explain. That's another table similar to the one that we were just talking about. Okay, when you guys go there, you only use this table, which is the A, only if the primary or the secondary or not and more than 600 volt. More than 600 volt. Is the primary or the secondary more than 600 volt? Yes. The primary, yes. Then you can't go to the B, to the table that says B. You have to go here. How do you use it? This one says any location. This is supervised locations. What's a supervised location? Supervised location when the building has its own crew of qualified maintenance electricians sitting there maintaining and troubleshooting and monitoring the system at all times. Industrial plants and what's not. All other application, so this is supervised. You don't go to supervise unless you know it's supervised. So any location, your default is any location. Your default is any location. So if the primary, so you have primary protection, secondary protection. If the primary, then you have to go fuse and circuit breaker. The first row is the impedance 6 or less, not more than 6. That's your default. If you're circuit breaker, you go 600. If it's fuse, you go 300. I want to bring to your attention, guys, note number 1 here and here. What does note number 1 say? You don't hit the standard. What do you go? You go up on the primary side. On the secondary side, guys, if your secondary is 600 volt or less, exactly like mine here, you're going to use 125. And do you guys see a note number 1 too? Yep. So what do you do with note number 1? You go up. Any comments, any questions? Comments, questions? You guys have your code book with you? Okay. Why don't you highlight these tables in it? Highlight the stuff in it. Make sure you know how to use this table, because when it comes in the test, that's the one that you're going to have. Any comments, any questions? Any comments, any questions? This will be PDF too for you, so it's any comments how to use this table, guys? Why did we go to this table, not the one before? Because the voltage on the primary side is more than 600 volt. The voltage on the primary side is more than 600 volt. Before we leave this topic, I will remind you guys, we go into any location, we go into the first row, the impedance is the 600, circuit breaker give you 600, fuses 300. I'm using a fuses atom on the primary, so I use 300. On the secondary side, I'm using circuit breakers or fuses, doesn't matter, but the voltage is 600 volt or less, so I use 125. And both of them have note number 1 right here and right here. So so you can go up. Any comments, any questions, guys, about this table? Comments, questions about this table? So that's to size your fuses. So let's go ahead and size the conductor first. We'll do that when it comes to the fuses. All right, so how do you size this? We've got your transformer. Here's my 1500 K. Divide this one by 4160 times 1.73. When you guys go there, that will get you a healthy 208 amps. 208 amps. Very easy, straightforward. We're going to assume that it's a continuous load. Again, assume it's a continuous load. So multiply this one by 1.25 and 208. That will get you a healthy 260 amps. And then the 260 amps, you're going to take it to 310.60 C77 under 90-degree column. Now this is new. I want to remind you guys that the cable that we're using on the primary side is a high voltage cable. Can I use the 310? Can I go to 310.15B16? Not anymore. I can't do that. I can't go to 310.15B16 anymore. I have to go to 310.60C77, and you have to go to and we go to 90-degree column is your default. When you guys go there, I'm going to show you in a second how this table looks like. When you guys go there, you're going to end up with 3 conductors of number 4 at AWG, and the installation is called MV-90. Now, Dirk, I don't know if you've ever heard of MV-90. MV-90, guys, is a medium voltage temperature rated for 90 degree. Why did we use a medium voltage temperature rated? Because look at the voltage, 4,160 volt. Can I use THHN? No. Why? Because THHN is not rated for more than 600 volt. Did you guys hear me? EHHN wouldn't cut it here. Okay, here's the table that you get this. Here's the table that we went to. Okay, this is the table. Please highlight this table. That's the one I'm going to go to. It says 3 single insulated copper conductor in underground electrical duct, 3 conductors per electrical duct. So that's the assumption. The assumption is you're going to put them in a conduit underground, 3 conductors. That's not in the air, in underground. That's typical installation. Okay, I want to bring to your attention, guys, how to read this table. None of you probably have ever been here. The first thing you need to pay attention to the voltage. The voltage here goes to up to 5,000 volt. The second set of columns goes to up to 35,000 volt. So if your system is 13,800, you're here. If your system like the one that we're using is 4160, so I'm right in here. Everybody knows why I went there? Then I have 2 options. Either go MV 90, 90 or 105. What's your default? Unless you know otherwise, 90. So we go to the 90, MV 90, and then here's my amps, and here's my conductor. Why didn't I go to this side? Anybody? Because the voltage, my voltage is not within that range of 5,001 to 3,500. You're going to go where your voltage range is. Why didn't I go to the 105? See, you don't go to 105 until they tell you the cable is rated for 105. I didn't tell you, I told you, I didn't tell you anything. So you default to where? To the 90-degree column. Can you please write yourself a note of that thing? This is how they do it, guys. They're called detail. This is based on detail 1. Detail 1, what they do is they have 11.5 by 11.5 inch concrete for these medium voltage, and they have a duct, a conduit encased in concrete to protect the medium voltage cable, and they put it underground. When you look at it, it looks something like this: a conduit encased in concrete with 3 conductors inside it. Each one of them is 4 aught. And the installation is medium voltage -90. You probably have never heard of that or seen that. So, and very few of you, when you guys work, Karen, probably you, if you're part of the lucky ones, maybe 5% of you will be dealing with this. Most of what you guys are going to be dealing with is 600 volt or less, but Mishad does a lot of stuff, typically engineers, but you guys could be the engineers doing that work. Any comments, any questions? What detail 1? These are from any secret book, guys. Detail 1. This is how it looks like. It's basically, I don't know if you guys, 11.5 by 11.5 inch. Imagine a cube of concrete, 11.5 by 11.5. Right in the middle of it is a duct, PVC, Schedule 80, surrounded by that concrete, or any duct that they make, concrete ducts, is surrounded by concrete. And you're pulling all these medium voltage inside it. Why would we do something like this in medium voltage? Do we have to do it this way? No. That's one way of doing it. Here's another way. You can bring 3 circuits, each one of them in a duct, 3 circuits like this, right in here. You could have 6 circuits here, oriented this way or this way or this way. So there's so many details. So when you guys go to this, want to bring to attention, where's when it says detail 1, can you guys see that detail 1 here? That's a detail that this table is handling. Every table has its own detail. What is a detail? The way that you're going to pull these conductors underground. Is it directly buried? Is it 1 circuit? Is it 5 circuits? So depending how your system is, for you at this level, with me, you're going to be dealing with detail 1, the easiest detail. But it's really not rocket. If you love aluminum so much and you can't live without, this table here is for aluminum. Same table, it's just except aluminum wires. Any comments, guys? Any questions about this? So everybody knows where we came up. You can't believe how many times over the years I taught, and at the end, when the student size in the test, they go to 310.15 B16. You don't go to 310.15 B16 if the voltage is higher than 600 volt. Can't go there. If you look at it, you can't go there. Okay, so we got that one. Everybody knows why we went to 310.60.60C 7790. All right, so we got that under control. Everybody knows the fuses. Now we size the cable. Reminder, I'm using a fuses on the primary side. And what's the multiplier atom for the fuses? Looks like 300%, right? So remember that where the 300 came. On the secondary side, you guys remember what the multiplier here? 125. Fuse or circuit breaker, I don't care here. Here they distinguish. If it's a breaker, they do 600. If it's a fuse, they do 300. Does both of them have node number 1? Yes. What does that mean? You can go up. Okay. Now, armed with this information, let's go to the next standard. So, I'm going to go multiply 3. Anybody knows why 3? The fuse. 208 multiplied by 208, the full load current of that motor, give me 624 amp. Since they don't make 624 amp fuse, so I have to go to 240.6. Gentlemen, and you are dealing with a 700 amp. You can go up to 700 amp. Do you have to go up to 700 amp? No. On the test, what should you do? You have to go with me on the test to the next standard up. In real life, it's up to you to go. You can go. You still can do it down if you want to. You know, going up is an option, not a must in the code. Okay, so that's my my fuse, and this fuse, by the way, will be most likely 5,000 volt rated. So this is a big fuse. It will be a 5,000 volt rated fuse. 5,000 volt rated fuse. Not 600 like the other fuses. Okay, moving into the secondary side, guys. Secondary, piece of cake, you take the 1500 K divided by 1.73 times 480, and it will get you a 1806 amp. 1806 amps, if you do your math on this. We're going to assume it's continuous load. Again, big assumption. 1.25 multiplied by 1806. That will get you a healthy 2258 amps. And 2258 amps, we're going to go parallel them, guys. 5 sets. I'm going to do 5 sets. If you do 5 sets, that'll get you 452 amps. And if you take this one to table 310.15 B16, because under 75-degree column, because that's low voltage, that will get you 5. Here's your conductor will be 5 sets, because we're parallel, of 3 conductors. Each one of them is 700 kcm THHN. So that's the phases for this system. Your phases for this system. Now the neutral, for the neutral, guys, let me use the neutral. When I use the same calculation for the neutral, I get the same amps neutral, because I do have a neutral here. So I will take 200 to 58. Let's take the first 200, leave them alone. Take 258 minus 200 and multiply them by 0.7. Add everything up, and you're going to end up with 1641 amp. And then take the 1641 divided by 5, because we also have to parallel them. That will give you 328 amps. And from here, take it to 310.15 B16, 75-degree column. That will get you the same thing, guys. 5 sets of the conductor, 5 sets of one conductor, 400 kcm THHN. Five sets of one conductor, 500 kcm, 500 kcm. Any comments, any questions, guys? Any comments, any questions? Comments, questions? A lot of wires, a lot of cables. A lot of wires, a lot of cables. Tons of money. Good. Okay, let's go to the fuse or the circuit breaker, guys. That's number 4. For the fuse or the circuit breaker, 1.25, same thing. Multiply that baby. That's from NEC code book by 1806 from the table. That'll get you, gentlemen, 228 amps. You take the 2258 amps, take this one to 240.6, and you go to 2500 amp. Your next non-adjustable circuit breaker will be 2400 amp. Now, what they do, guys, typically, you go to that circuit breaker, Karen, and you tweak it down to match your conductors. Did you guys hear me? You go to the circuit breaker, because we size our conductors to 2258, right? And adjust that circuit breaker to match your conductors. That would it make a difference if it's circuit breaker or fuse here? No, in the secondary side doesn't make a difference. On the primary side, the high voltage, you have to decide. If you put a circuit breaker on the primary side, guys, you have to multiply by 6. If you put a fuse, you have to multiply by 3. Major difference. That's the difference between having a 600 amp fuse or a 300 amp fuse, or a 600 amp circuit breaker or a 300 amp fuse. Okay, separately drive system, guys, 250.66, 250.38, 5. These are the grounding electrode conductor. Let's go size that baby. For the grounding electrode conductor, guys, I have 5 sets. You multiply them by 700 kcm, and that'll get you 3500 kcm. You take the 3500 kcm, take it to 250.66. That will get you a healthy one conductor, 3-aught AWG THHN, or Mr. Bear. THHN or THHW or Bear conductor. This is a grounding electrode conductor, that takes the guts of the neutral and tie it to the ground bar. Now this one will take actually the ground bar and tie it to the ground rod. Now we need to go to the bonding, the main bonding jumper. Any comments, guys, about number 5? That's the one that goes to the steel of the building, to the ground rods, and what's not. Good. The last thing we need to size for this baby is the main bonding jumper. The main bonding jumper, gentlemen, you do the same thing. You take the 5 multiplied by 700. That will get you a healthy 3500 kcm. Then, since the 3500 kcm is more than 1100 kcm Cu copper, this is your copper. Since this number is more than 1100 kcm, now we will trigger the requirement of 12.5% multiplied by 3500 kcm. And if you do the math on this, you end up with 438 kcm. 12.5% multiplied by 3500. And I don't know about you, Adam, but they don't make 438 kcm in the market. They don't. It's not standard. So in a case like this, what do? You take the 438 kcm, take this one to chapter number 9, table number 8, NEC. NEC, chapter 9, table 8, gentlemen, and that will get you one conductor number 500 kcm THHN or bare. Okay. Now your system will look something like this. Can you guys see the secondary system? 1, 2, 3, 4, 5 conduits, right? 5 conduits. I want to quickly remind you guys that these conductors here, let's use this. These conductors will be, what did we say the conductors here? 700 kcm. The neutral guy would be, what did we say the neutral came up to be? Was it 500? The neutral guy came up to be 400. My neutral guy came up to be 400 kcm. That sounds like a mess, huh? Trying to fit that one. 400 kcm. So you're going to have a conduit with 4 conductors, 3 of them the same size, 700, and the fourth one is 1 conductor with 400 kcm. The one with the calculator, let's go size that baby.
Does that say
250.38 and this is my and.
Oh, 38.1?
38.1 and 3. 1 and 3 tops already. 250.66. These are the references that you guys have. The last thing I'm going to do, guys, I'm going to take go size with the calculator that you have, size the conduit here. So grab your calc. Where's my calc? There you go.
We've done all this that we just did on this calculator.
Absolutely. Well, you have to know what you're doing, medium voltage. Okay, let's just size the conduit and I'll show you. Let's go size the conduit, guys. 6, sit at 7. Make sure you click sit 7 so you can set your calculator at 3-phase 75 copper. Okay? So make sure your calculator is set at 3-phase 75 copper. Yes? The ones who have it? Okay. We need 700 kcm. So here's how you do it. Hit 7, 0, 0, another 0. For kcm, you hit the K here to get you. Can you see that right here? This is K. And so 700 kcm, to tell it it's a wire, then you hit that wire. So now the calculator knows it's a 700 kcm wire. Cool? Can I have thumbs up, Chad? Yep. Next. How many conductors do we have of them? Remember, there are 3 of them. So hit the number 3. Then you ask yourself, what type of insulation are they? THHN, hit THHN, right? And hit THHN again. That will give you the cross-sectional area of all these 3 conductors. It's 2.9661. If you hit THHN again, guys, it will give you how many conductors and what the cross-sectional area. If you keep just hitting it, it keeps giving you the number of conductors. Cool? Now we're done with the 3 conductor. I need to add 1 more conductor to it, right? Different size. So here's how we do it in this order. What's the size of the other conductor? 400, 400. Okay, what K, here's my K, and hit the wire size. Now I told the calculator, please add another 400 kcm copper to the conduit, but I didn't tell her how many of them yet, did I? How many of them do we going to have? One. So you take a one, and you're going to put it in a THHN. I hope we have a conduit, right? THHN, hit again, and hit again, hit a couple of times here. So that will add the cross-section area of one conductor 400 to the three conductors of 700 kcm. Cool? I hope we have a conduit that can fit these. Otherwise, you just parallel. And now we're going to go hit conduit. Okay, I have conduit of 3.5 EMT conduit. Can you guys see that? Did you come up with the same answer? Okay. Now you say you change your mind and you need to go PVC, right? Just one PVC. If you guys go to the back of your calculator, it has PVC is number 9. Can you guys see it? The top PVC is little number 9. Okay, 9 is PVC. Here's what I would like you guys to do. Then hit 9 right away. 9 and conduit. Oh, I'm sorry. 9 set conduit. ENT. I think I screwed it up. I should have. I think I just screwed it up. So, but you got it, yeah? Right set. There you go. There you go. 4-inch. 4-inch PVC. 9 set conduit will get you. If you need rigid, what was the rigid number? Rigid metal conduit is 8. So hit 8 set conduit. 3.5 rigid. See how nice this is? Not only you can give one conduit, but you can easily flip between one type of conduit to another. Isn't that cool? Okay, the last thing I'm going to do before I give you is size the stuff. So here's how this is. This goes, guys. Suppose I want to size. Let's go back here, and I want to size my. What am I going to size? Let's just size. I'm going to go size my primary fuses. You have to tell the fuses. Conductors. Here you go. Primary conductors. Let's try sizing the primary conductors. Can you guys see that? Here's 1800. I mean these are secondary conductors. Okay. So type clear, go clear, will ya? Hit clear a couple of times. Then go type 1806. This is how much amps you have for this transformer in secondary, right? And then since it's going to be, I'm going to multiply it by 1.25, type set and wire size. It's telling you, have you lost it? There is no wire that can carry this amount. Okay? Now you're going to tell you, how many do you want to parallel? 5. Then type 5 and hit, you can see parallel size? Everybody can see that? Parallel size? Hit parallel size, and it didn't give you. 5 parallel size. It didn't give you that one. So I don't know if we got, oh, we didn't put the amps. Did we? Oh, I'm sorry. We have to put amps first. We put them as amps. One more time. Let's take the 1805. Did we type amps? Did we click amps? I don't think we did. Click amps. Now we're talking. Now you identified these as an amp. Okay? Then go set, hit set, and wire size. It tells you there is no size that can carry this. Why did I put set? If you put set, wire size is size based on 125%. Can you guys see that? Okay, now then I'm going to go parallel. Then hit 5 and parallel. And what did we come up with? 500 kcm. What was my size before? Was it 700? 5 sets. We came up with, why did I come up with 700 here? It's sizing it based on 500 kcm. 500 kcm. Interesting. 5 sets, 500 kcm. Well, if you, yeah, I don't know if they take into consideration, sometimes when you put them by each other, 5 sets, you can't use directly the table, you have to go to other tables. Yeah, this is an extreme case where you know, you're pedaling. If you're pedaling, you might have to check your work, but came up with 500 kcm. But we have to size it though 452, more than that. I don't know why we came up with 500 kcm. I want to use, now it's made me curious. Let's take 2558. Do the multiplication ourselves. Can you see that? I'm just going to take that number and ambit, and then wire size, and then take 5 and take the pedal. 900. Wow. Yeah. 5 sets, 900. Is this 700 the right connection? Maybe I made a mistake for this. 452 amps. Wire size 700. Yeah, 452 amps. See, if you do the math here yourself and you just put the 452 amps and you hit the amps, it will give you the right calculation. But somehow for the pedaling is not picking it up. So if you just type 452 amps and wire size, bam, it gets you the 700. So to be continued. Before I let you guys go, let me get you. I need to have homework. The homework that I would like you guys to do is please grab that. So grab, here's your homework. Write on number 2, exactly like number 2, right here. I'm going to say example 2, homework number 1, example number 2. All what you have to do is, here's a primary, here's a secondary. You guys are going to size the same thing for these babies. The only thing I'm going to give you is this one is going to be 1000 kVA. The primary is going to be a 4160. Oh no, 13.8. Let's use this one, 13.8. The primary is 13.8 kilovolt. The secondary, I would like you to use this one, guys, on 600 volt. 600 volt. Size, what do you need to size? Size the 5 things. Size the 5 things, right? Everybody knows what the 5 things that we need to size? The conductors, the fuses, the grounding and bonding. I'm going to say size the 5 things. And everybody knows what the 5 things are. Right? Okay, so I think our speaker is going to be here shortly, guys. Or he just called not to show up.